Okay, so I will present you some observations and some lessons that we can take from the Permian rift system that is well documented in the Alps, and that gives insights on some aspects on rifting magma-rich systems. And of course, this is results that is not only made by me, but also by collaborations with many colleagues. And in fact, if we take some examples of rift domains, even those that are not well known for magmatic intrusions, magma additions are quite often documented, even if not expressed in the volcanic basins. If we take, for instance, the results of refraction seismics across several rift domains, we see that based on the refraction profiles that the authors are showing, that mafic additions in the crust is quite often documented. And in fact, if we take just on the other side magmatic systems like the Talkeetna, the Karoo, or the Yellowstone, only a third of magma is making their way up to the surface, and quite a lot is trapped in the continental crust. And of course, if we do this while extending the crust, this has a strong impact on the answer on the crust to extension, because these magmatic additions can have the potential of limiting the continental crust thinning during rifting, either if it's focused, like in this scheme that is implemented from Bloch and Royden, or in case of crustal flow that is triggered and that may be triggered by magmatic additions in case of localized intrusions, for instance. And this brings me to the fact that magmatic additions can limit crustal thinning and can soft the continental crust during rifting. And of course, understanding the way magma interact with continental crust is quite important, because if we take, for instance, the numerical models here of Gueria and Burg, depending on the density and rheology of the lower crust, magmatic system will not be constructed the same way. For instance, if we have a cold and mafic lower crust, we will have more seal type intrusions, whereas if we have cold and felsic on hot and mafic, we'll have more finger type intrusions. Whereas if we have more hot and felsic lower crust, magmatic additions that is sourced in the mantle will be trapped in the lower crust, indicating that the lower crust is acting as a real buffer for magma in this case. Therefore, we should keep in mind that here we have instantaneous emplacement of tolithic melts. And of course, magmatic systems are a bit more complex, and we know that they are growing incrementally, that they are characterized by a mushy reservoir where we have crystals and melt together, and that have complex rheologies de facto. So I will address a few questions here in the talk. First, how is magma transferred, and to show how is magma transferred in a natural system. Why is it stopped in some extent? And how are the underplated magmatic bodies constructed, and how they interact with the continental crust, and how continental crust is behaving in case of magmatic additions. And to do so, I will not take an active example, a present example. I will take us back to the Permian in Western Europe, where we had, after the Variscan orogeny, we had a widespread crustal reequilibration, where late to post-Variscan processes were accompanied by lithospheric extension and mantle partial melting. And we see this by, for instance, here looking at a map of Permian basins, where we see fault-bounded basins that are intracontinental and really elongated, and that are sometimes filled by volcanics, both mafic and felsic. And this was followed by long-term subsidence during the Mesozoic. And we had the chance to have the opening of the Alpine Tethys and the Atlantic system, where these rocks at depth were brought to the surface, and where we have now access, in fact, to a whole crustal profile. In fact, we can rapidly draw this type of scheme from the Permian system that is outcropping in several places, where we have from the base of the crust to the top, we have mostly mafic intrusives at the base. We have both mafic and felsic intrusives in the middle crust, and in the upper crust, mostly felsic intrusives and extrusives that were placed in the Permian in a continental crust that was also quite differentiated at the time. And to demonstrate this, I will go to the Alps, and notably to visit a few outcrops there. And basically, there are two major domains where we are able to reconstruct the continental crust. The first one is Southern Alps, where we have low alpine deformation, and we can see a quite pristine section of the continental crust. And the other one is in the Eastern Alps, here a bit north to the incline to the east, where we have stronger alpine deformation, but still we are able by reading the content of the different names and sometimes going to places where alpine deformation was not really pervasive, that we can also reconstruct several steps of the construction of the continental crust. Basically, this will be the two examples I will show you. The Southern Alps with the well-known Ivrea mafic complex up to the Mesozoic basins that are to the east. And in fact, we can see a complete cross-section across the crust from the sedimentary basin, the upper crust, the middle crust, and the lower crust down to the Paleomoro almost. And the same observation can be made in the Eastern Alps, where we have to the west more mantle units, and we have to the east more upper crustal units with mid-crustal units that are lying in between. First, the Southern Alps, in fact, are quite well preserved, and we can see that if we make a cross-section across the Ivrea mafic complex, that is this potato there, and a bit north to the Ivrea mafic complex, that we can still see with by making pressure and temperature estimates here compiled by literature data, that we are still able to find the lithospheric pressure gradient of 0.3 to 0.4 kilobar per kilometer, whereas to the north it is more deformed by subsequent deformation, and therefore you will see that we'll essentially focus to the south by tilting a bit the map for convenience and presenting the map in such a way that we are going from the surface with a rhyolitic volcanics. Here, for instance, the Indemite breccia. Then we have in the upper crust several granitic intrusions, the Rocca Pietra, Vallemoso, also Baveno and Montorfano granite. And then we have the CMB line, that is a major Permian shear zone that we'll visit a bit afterwards. And we go down to the Kinzigite formation, that is a metasedimentary lower crust, where the upper mafic complex and the lower mafic complex were emplaced during the Permian. And here a few pictures of the mafic complex with a very nice gabbro and sometimes with pyroxenite layering and so on. And if we take just a compilation of a few ages, we see that we have a synchronous magmatic event from the volcanics to the granite and the gabbros. And we can rapidly estimate the surface of the different extrusive and intrusives. And we have, again, only a third of magma that made up to the surface. And we should note that there is a pre-existing high-grade metamorphic event at 310 million years that predates the emplacement of the mafic complex. And same observations can be made to the east, where we have, again, a gabbro that is emplaced in the lower crust at the contact with the mantle. We have in the middle crust intrusives that were emplaced in sedimentary units, the Campo unit. We have in the upper crust, again, volcanics that are filling fold-bounded basins, like here to the northeast, but also here a bit more to the south, where we have very nice preserved rhyolitic flow bending with thin magmatic flows, and faults, and also that are floored by high-grade mylonitic shear zones of unconstrained relation with the basin. Now, what is important is to visit a bit the way intrusives are constructed in the middle crust. And to do so, we'll visit the Sandalo-gabbroic intrusion, where we see that we have a host rock that is very nicely foliated with steep foliation that is deep into the northeast, that is of a Variscan age. And the intrusion of Sandalo, that is Permian, is characterized by olivine gabbro in the center, gabbro, and then diorite to the border. And we can still see rafts of metasediments that were incorporated in the Pluton, with very elongated xenoliths that are still preserving the orientation of the foliation of the host rock, as we can see here, that is steeply deep into the north or to the south. And parallel to these xenoliths, we have sheets of gabbro that were emplaced with magmatic fabric that can be seen in the field, like this picture, and also at the micro scale with a shape preferred orientation of hornblende and pyroxenes. That's the main fabric.
10 minutes now, Benoit.
Okay, and that's the fabric of the center of the Pluton. And then in the rim, we have a new fabric that is rimming completely the intrusion. That is dated at 385 approximately million years, whereas in the center we have a bit much older ages of 289 million years. And this indicates that we have a sequential growth of the intrusion with dikes that were emplaced in the first stage, with dike-controlled emplacement that creates the sheets also that we can see in the field. And then we have the coalescence of several dikes that constitutes most of the core of the intrusion, whereas in the rim, we have a ductile aureole that characterizes the late stage of magma emplacement, indicating that in the first stage, we are controlled by dike emplacement, whereas in the subsequent stage, we have more ductile deformation of the host rock. And this is caused by the different rheological limits we have with in partially molten system, where we have, when crystallizing a gabbro, a threshold that will occur at around 1,000 degrees, whereas the melting migmatite will have a switch of rheology, decrease of viscosity that will occur way below. And this will allow to identify the host rock, whereas the core of the intrusion behaves as a more rigid and a highly viscous body. And similar observations can be seen in the southern Alps, where we have strong host rock deformation, probably pre-intrusion, with partial melting, and that was dated at around 310 million years, whose duration is still a bit debated. By contrast, if we go in the migmatitic shear zone, we have highly sheared migmatites with, for instance, here that we can see. And this highly sheared migmatite is really narrow, is a narrow zone of strong host rock deformation, as we can see here with antithetic faults, indicating that we have host rock deformation, but it's, again, quite geographically restricted. We have also deformation at the base of the intrusion, whose relation with the emplacements is quite unclear. And along the CMB line, and this is quite a strong message that I want to highlight, we have also magmatic additions expressed as small veins, but these are really short veins that are really thin. And seeing at their thickness, they estimate the magma present to be only kilo years present in the system and not present during a long period. And similar observation can be made if we go just up to the CMB, just above, where we have multiple melt injections, and they determined quite recently that the melt present growth of crystal is quite short-lived again, with garnet, for instance, that were overgrown 2 times, with melt presence during a few kilo years only. This indicates that, again, even if shear zones are lubricated by melt, the melt present is quite short-lived. And then this leads me to the way magmatic intrusions are constructed in these systems, where most of the melt is placed in a quite narrow time span. In fact, recent ages by Caracas dated the emplacement at 383 million years in only 2 to 4 million years for the bulk magmatic system. And therefore, the construction of these underplated mafic bodies is quite short, occurs rapidly, with host rock deformation that is quite restricted, and the melt that potentially lubricates shear zones is quite short-lived also. And of course, we can go a bit more in the story on how this complex was constructed, but we have a strongly re-equilibrated magmatic fabrics, and therefore we should go with a more detailed analysis of the magmatic fabrics, as for instance with tomography that we are performing now. And finally, the lesson is that the incremental growth of magmatic bodies, of magmatic intrusions, is accommodated by localized host rock deformation, that we have variable magma transport mechanism in these systems, and the relation with tectonics is quite important in pumping them, in driving the melt, but melt in these shear zones is quite short-lived for lubricating these shear zones. And of course, this has some importance also for subsequent deformation, as it will completely change the rheological profile of this continental crust by adding mechanical heterogeneity that will control and partition the deformation. And this is one of the aspects that will be covered by an ICDP project we have in the Southern Alps, the DIVE project, that will go on next year probably. And that was probably the only messages I want to tell today.
Thank you, Benoit. Can I remind attendees, you can type questions for Benoit in the chat, or you can raise your hand and you can ask them yourself. I think you've shown a lot of, at least for me, a lot of field pictures. It just makes me want to go to the field, which I haven't done in a very, very long time. I think like a lot of the audience probably. So does anybody have any questions? We're a little bit over time maybe, so we can always leave them to the end as well. If people don't have an immediate question. Maybe it's taking everybody some time. So, okay, Kim has a question. Go ahead.
I'm just curious, in terms of the timescales, it looks like it's really nice and short, but what kind of volumes, like proportion of the crust is taken up by these magmatic intrusions, would you estimate?
Well, it really depends where you are, in fact. For instance, if you, well, let me take probably this slide. Yep. If we are in the mostly mafic part of the Ivrea zone, we have most of the crust that is magmatic, in fact. Like we jump here directly from the gabbros to the granite and to the volcanics, where we have almost only magmas. Whereas if you go a bit more to the north, and here we have mostly felsic lithologies with granulite and metasediments. So it really depends on where you are, in fact.
I also see Robert raised a hand. Would you like to ask a question yourself?
Yes. How do you discriminate between magmatic and high-grade metamorphic fabrics?
That's a really good question, in fact. And the thing in the literature, it's also not clear in the Ivrea zone, because most of the mafic complex is reported as having as being granulite mafic rocks. But in fact, these are just gabbros that were cooled down very slowly at high temperature. And most of the fabrics are in fact re-equilibrated, but this is only because we are crystallizing the gabbro slowly. And in fact, well, we can see that I don't have pictures here, but we can see veins and dikes that are cross-cutting the base of the mafic complex with non-equilibrated textures, with a nicely elongated plagioclase and this type of features. So in fact, the transition is progressive. And I may show rapid picture of preliminary results we have using the tomography. And in fact, we can assess the shape of the crystals in a detailed way and quantitative way. And in fact, we see that here we have the degree of anisotropy of the fabric. And systematically, the anisotropy is really reduced when we are at the base of the mafic complex because of this high-grade re-equilibration of the fabrics. But this is the normal evolution, I would say, of a gabbro that is crystallizing in the low crust.
Yeah, I think in the interest of time, we ought to move on, but there are a couple more questions in the chat. So Benoit, if you wouldn't mind answering them, that would be great. You can just type your answers.
Sure.
And we can move on to our next speaker, who is